Thanks. Yeah, this is joint work I did together with Elia and Gillard, and another paper I did with Kun and again Gillard. So I will begin with a short motivation. Why are we interested in state convertibility? And why are we interested in the specific conversion distance that we will use and how it will come up? Then I will give you a precise definition of the state conversion distance. And I will talk about two applications, namely to embezzlement, to distillation and dilution of pure states. And then in the end, I will also quickly talk about the entanglement cost of mixed states and channels and how this is related to the star conversion distance. So the state convertibility is at the core of entanglement theory, or more generally at the core of any resource theory, right? Because it determines a relative value of states. So let's say if we have a state rho, then knowing to which other states we converted with the help of LOCC is important because it essentially tells us how we can use the state, right? Let's say we have a specific protocol that requires the use of sigma. For example, if we want to send n bits safely, we can do this with LOCC and sigma. Well, then we can also do it with rho if we can convert rho to sigma using LOCC, right? Because then we can first convert rho and then use exactly the same protocol that uses sigma. But in general, it might be possible to do better. For example, to send more bits by using a different protocol because it's not clear that the protocol that first converts rho is optimal in any way. So studying state conversions determines the value of states and is therefore very interesting if we think about applications. Now, what happens if we cannot convert rho to sigma, right? But we would like to use sigma for an application. Well, then we can ask how close can we get to sigma? And because, well, since quantum mechanics is linear, right? If we can get very close, then there's a good chance that we can do something similar. Maybe if we can get arbitrarily close, we can send the same amount of bits or something like that. Now, for this to work, we need to have a definition of closeness, right? How do we measure the distance between two states? For example, we can use the trace distance, and then we can use the trace distance here to define the trace conversion distance. So we say, okay, we essentially ask how close can we get in trace distance? Now, if we consider pure states, so if both the initial and the target state are pure, then of course we can use exactly the same definition. There's no problem. But in general, the closest state that we can reach, right, the state tau here, is not pure itself. It might be a mixed state. So therefore, we can also ask, well, what's the closest pure state that we can reach? And why would we want to ask this? Well, for technical reasons, this would make the problem much easier, right? Because we know much more about pure state entanglement transformations than about mixed state entanglement transformations. And in general, we can also use different distances, right? We could use like a purified distance or something like that to measure the distance between states. And what we will use here is, in fact, another distance. So what we looked at is what we call star conversion distance. So here we restrict ourselves to pure states, right? Because this will allow us to get much neater results. And in particular, well, we define the star conversion distance like that. Now, what are the quantities that appear here? So everything bold are probability vectors. So P is the vector, probability vector that contains the Schmidt coefficients of the initial state. Q is the probability vector containing the Schmidt coefficients of the target state. And R is the probability vector over which we optimize. And while the way in which we optimize is we optimize over all vectors R that majorize the vector P. So majorization, well, you may be familiar with it, right? It's just a pre-order on probability vectors in this case. And it's equivalent to saying that the Q-Fan norms for all k between 1 and the dimension of our probability vectors, they are, well, larger on P than on Q. So Q-Fan norms is essentially just a fancy way of saying we add up the k largest entries of this probability vector. And well, they will appear a lot in our formulas just by the way how we construct the star conversion distance. Now, why is this a meaningful definition? Well, we don't know yet that it's meaningful, but the intuition why we are interested in it is because of Nielsen's theorem, right? because we know that for pure states, we have this if and only if condition for state conversions if we have a majorization relation. So essentially R is the vector of Schmidt coefficients of the closest pure state, and closeness, well, we define here on the probability vectors instead of on the states. Now, this is so this is not in trace distance, right? But it's essentially in trace distance. So the star conversion distance and the trace conversion distance, they are topologically equivalent in the sense that while if one of the two goes to 0, the other one goes to 0 as well, right? So whenever we talk about something where we want to send the arrow to 0 anyway, it doesn't really matter which of the two distances we take. And well, the second nice property is that we can have closed form expressions for the star conversion distance. And essentially the tool that we use is some results on approximate majorization. So here we have again these Q-fun norms, right, on P and Q, which are again the Schmidt coefficients of the initial and the target state. And then we just need to do a maximization over a finite set. So K runs over the integers from 1 to the Schmidt rank of the initial state. And well, this will allow us this closed form expression will allow us in the applications. So the first application is to entanglement embezzlement. So according to Van Dam and Hayden, we call a family of pure bipartite states universally embezzling if, well, this equation here holds. So essentially, we take the trace conversion distance in the original definition, we take a member of this family, chi n, and then we convert it approximately to the state itself and a copy of the state we want to embezzle. So this is why it's called embezzling, right? Because we can essentially borrow the state chi n, then we steal the state sigma from it and return the state chi n. And in a limit, this is not detectable, right? Because the conversion distance goes to 0, so also the state psi n will, in the limit, not be changed. So this is the definition. Now, with the star conversion distance, we can replace the trace conversion distance here, right? Because like as soon as we send the arrow to 0, it doesn't matter which of the two distances we take. So, okay. Okay, so now with this closed form expression for the star conversion distance, we can also find an expression or a condition when a family of states is universally embezzling. So this may look a little bit complicated, but it's much simpler than asking just can we get any state from it with LOCC, right? Because we only have, again, Q-fun norms, and then we also need to do, like, again, this maximization over integers in this case. So in particular, this allows us to study in which sense the original family of universal embezzlers introduced by, well, Van Dam and Hayden is unique. So the family that you see up there that they introduced is, well, they showed in their work in 2003 that this is a universal embezzling family. Now, a very simple generalization is, well, we don't take this factor of 1 divided by square root of x, right? But we put some other factor in front. For example, you can put a square root of x to the alpha. And then this condition on the previous slide allows you to show, well, such a family is a universal embezzling family if and only if alpha is equal to -1. And the reason is, well, with this closed form expression, for alpha larger than -1, you can directly calculate the star conversion distance, well, from a member of this family to itself and a maximally entangled 2-qubit states. But it's also quite easy to show if you can embezzle a 2-qubit maximally entangled state, you can essentially embezzle everything. And while for alpha smaller than -1, you can find lower bounds from the previous expression and you can bound away this conversion distance from 0. And I don't have time to talk about it in more detail, but this was a very simple example. But you can show much more. You can show that essentially this family is unique up to, well, under very reasonable or very weak assumptions on your states. For example, that the coefficients are asymptotically non-increasing. You can show that every family of states must be very close to this original family. And yeah, for more details, I refer to the paper. And there are, for example, variants by Leong and Wang from 2014, but those are also very slight modifications of this family, and they fall into these conditions. So now let me come to the second application, namely to entanglement, distillation, and dilution. So let me call the maximally entangled state of dimension m, phi m, and then here I'm working in a single shot regime. So different to the previous two talks, I'm not talking about asymptotically many copies. I'm interested in approximate conversions of single states, and I'm also not using catalysts. So here I have the epsilon single shot distillable entanglement of a pure state. This is essentially, well, the maximum dimension of a maximally entangled state that I can approximate up to an error epsilon with the given state. And of course, I can also define the inverse or the reverse, right, which is the cost. So I'm asking what's the smallest dimension in maximally entangled states that I need to approximate my state up to an error epsilon. Now here, the conversion distance is given with the trace distance, right? But I mean, you can again use, for example, purified distance, or what we did here is we use the star conversion distance. And if you do this, again, the closed form expressions allow you to find closed form expressions for, well, the distillable and the entanglement cost as well. In fact, they are rather compact and simple expressions. So if you quantify the error differently, there are also known closed form expressions, right? One was done by Bartosz, for example, in 2019. If you do it like that, you get, again, a closed form expression where you have this Key-Fan norm of the vector that contains the Schmidt coefficients. Of course, the error that you allow somehow plays a role, right? This appears as well. And, well, again, you have this simple minimization over, well, a discrete set, where now the lowest value of k is no longer 1, but it is L, and L is, again, essentially the smallest integer such that this Key-Fan norm is larger than the error that you allow. And, well, for the entanglement cost, it's even simpler because, well, again, you find m that is given by the error that you allow and the Key-Fan norms, and then you just have to take the logarithm of it. Now, those expressions, they allow for a few interesting consequences. For example, they allow you to explicitly and efficiently compute the distillable entanglement and the cost of multiple copies, and efficiently in the number n. Now, the expressions on the previous slide, well, you can explicitly evaluate them, right? Because you just need to sort probability vectors and take Key-Fan norms. Now, in general, if you take n copies, the elements in your probability vectors, they grow exponentially, right? The trick is the number of different entries does not grow exponentially, and this allows you to find algorithms, and, well, we have them explicitly in the paper. Now, another thing that is a consequence of this is that you can find second-order asymptotics. And this was, well, second-order asymptotics were, for example, found by Hayashi and collaborators in 2017, where they introduced those second-order asymptotics for a different error, a different way of describing this error. And while here, using essentially their techniques, you can also find the second-order asymptotics. So you have first, you have the asymptotic expression, right, which is just the Shannon entropy of your Schmidt coefficients. And then you get correction terms that depend both on the error epsilon. So you have a Gaussian cumulative distribution function phi, and they, of course, also depend on the number of copies that you have via n here, right? And, well, v is just the entropy variance. And also here, similar results have been known before, but like this, they get much neater, right? Because you use all this knowledge about approximate majorization. Now, again, here, this was the definition of the epsilon entanglement cost of pure states. Now, what happens if we want to go to mixed states? well, then we would need to generalize the star conversion distance to mixed states, but this is not straightforward because we use majorization to define it, right? So what we can do instead is we can go back to the original definition of Buscemi and Datta from 2011, and they defined it using the square of the purified conversion distance. And in this case, if you now want to go to mixed states, right, the purified conversion distance is defined for mixed state as well, so you can just replace the pure state with a mixed state. Now you might say, well, this is a bit, well, not good notation, right, because now I have the same, well, I use costs for two different distances, so at least on pure states, this should be conflicting definitions. But we will see in a moment that, in fact, the results equal on pure states. So in a bit of abusive notation, I will use the same symbol for both of them. So how can we find this? Well, already in the original work, they gave bounds on this cost in terms of entropic quantities. And it turns out these bounds, you can turn them into exact expressions by doing a slightly different smoothing. So we found that this epsilon single shot entanglement cost now of mixed states is given by the smoothed max entropy, conditional max entropy. How is this defined? Well, the conditional max entropy is just defined like that, where pi is the projector onto the support of rho. And then, as usually, you can smooth it, right? And in fact, we smooth it in a particular way. We smooth it with respect to an epsilon ball in trace distance. And this epsilon ball is over states, and it's not over subnormalized states, which is quite often done. And then the infimum is over all classical extensions of the original state. And classical extension here means we take a classical system X. If we trace out this classical system, we get back our state rho AB. In general, you can take this infimum also over all dimensions of the system X, the classical system, but the infimum is achieved if you take the dimension of X equal to the dimension of AB squared. So this essentially expresses the entanglement cost in terms of the conditional max entropy. Now, if we go back to pure states, this infimum here is trivial. So for pure states, we can express the cost in terms of just the max entropy. Again, the smoothed variant. So max entropy, the usual definition, right? Again, with the projector on the support of rho. And then, just as on the previous slide, we smooth it with respect to an epsilon ball in trace distance. And this has some interesting consequences, right? The first one the first one is clearly, right, this gives an operational interpretation to the smooth max entropy in terms of entanglement distillation of pure states. The second, you can find a closed form expression for this smoothed max entropy, and this coincides with the result that we found for the cost with the other way of measuring the error with the star conversion distance. And this also means that all the results I was talking about previously, right, they also apply here, right? The closed form expressions also apply for this original definition by Buscemi and Datta. Also, the second order asymptotics are valid for this case. And, well, obviously you also get that the two are the same on pure states. And, well, I don't have time to talk about it, but you can also extend these definitions to channels, right? You can talk about the epsilon single shot entanglement cost of a channel. So ask, how much entanglement do I need to consume in order to simulate a channel with LOCC? And, well, you can show that essentially also there with the conditional max entropy, you get bounds on the entanglement costs. So with that, let me summarize what I was telling you. So I talked about this new conversion distance, which is based on majorization. This allowed us to characterize entanglement embezzlement, and I gave you an example for a specific family. It allows us to talk about single-shot distillation and dilution of pure states with very nice consequences for closed-form expressions and second-order asymptotics. And well, I'm still not sure why, but it turns out this coincides with the cost with respect to the purified distance on pure states. Whilst for general states, it does not coincide. It's just if you go to, well, if your initial state is maximally entangled. Now, what can you do next? Well, I'm pretty sure analogous results should hold for other majorization-based research series as well, right? So a priori, I don't see why it shouldn't be possible to find or to define conversion distances in a very similar manner for coherence or thermodynamics. And I guess it might also be useful for other applications in entanglement theory, in particular if you want to send some arrow to zero anyway. And yeah, I also talked about a single shot entanglement, cost of mixed states, and how this is related to the smooth conditional max entropy. With that, yeah, thanks, and I'm looking forward to your questions.
Many thanks. Questions? Yes, use this one.
Okay, right. So you have this equivalence for cost. Do you have anything similar for distillation, or do you have counterexamples that you have the difference, the different distance will give you a different value of distillation for pure states?
No, we don't have similar results for distillation.
What do you know is not correct, or do you just know?
No, I also don't know that it's not correct.
Okay, thank you.
Yeah, but it would be interesting to compare this, yes.
Okay, thank you.